Prova. 1, 2, 3, 4, prova, prova. Sa, pronto, prova, sì. Chissà se... Prova. 1, 2, 3, 4, 5, prova. Prova 5, prova 6, 7, prova. Già verde, perfetto. Ok.
Punti di vista. Ah, ok.
Verde perché su
Oh.
Ah. Sa.
questo. Sì. Ma c'è il radiomicrofono?
Va aperto, adesso la regia lo apre,
Perché penso...
si inizia. Vuole parlare dal microfono asta o da seduto?
Ma c'è il radiomicrofono?
Va aperto, adesso la regia lo apre,
Perché penso...
si inizia.
Ma c'è il radiomicrofono?
Posto questo.
Va aperto, adesso la regia lo apre,
Perché penso...
si inizia. Vuole parlare dal microfono asta o da seduto?
Ma c'è il radiomicrofono?
Posto questo.
Va aperto, adesso la regia lo apre,
Perché penso...
si inizia. Vuole parlare dal microfono asta o da seduto?
Ma c'è il radiomicrofono?
Posto questo.
Va aperto, adesso la regia lo apre,
Perché penso...
si inizia. Vuole parlare dal microfono asta o da seduto?
Ma c'è il radiomicrofono?
Posto questo.
Miau miau.
Vuole parlare dal microfono asta o da seduto?
Ma c'è il radiomicrofono?
Posto questo.
Miau miau.
Vuole parlare dal microfono asta o da seduto?
Ma c'è il radiomicrofono?
Posto questo.
Miau miau.
Vuole parlare dal microfono asta o da seduto?
Ma c'è il radiomicrofono?
Posto questo.
Miau miau.
Ok, prova.
C'è il radiomicrofono?
Posto questo.
Miau miau.
Ok, prova.
C'è il radiomicrofono?
Posto questo.
Miau miau.
Ok, prova.
C'è il radiomicrofono?
Posto questo.
Miau miau.
Ok, prova.
C'è il radiomicrofono?
Posto questo.
Miau miau.
Ok, prova.
C'è il radiomicrofono?
Posto questo.
Miau miau.
Ok, prova.
C'è il radiomicrofono?
Posto questo.
Miau miau.
Sto miau miau, non so da dove arrivi. Io non ho niente acceso.
Ok, prova.
È sto roba che si ripete, ciclica.
Questo
Miau miau.
Un altro loop di là, diverso.
Non sappiamo da dove arrivi, non c'è un senso. Sto
Prova,
miau miau,
prova,
non so da dove arrivi.
prova,
Non
prova.
ho niente acceso.
ok, prova.
È sto roba che si ripete, ciclica.
Questo
Miau miau.
Un altro scusa, possiamo
Non sappiamo da dove arrivi, non c'è un senso. Sto
Prova,
miau miau,
prova,
non so da dove arrivi.
prova,
Non
prova.
ho niente acceso.
ok, prova.
È sto roba che si ripete, ciclica.
Questo
Miau miau.
scusa, possiamo
Non sappiamo da dove arrivi, non c'è un senso. Sto
Prova,
miau miau,
prova,
non so da dove arrivi.
prova,
Non
prova.
ho niente acceso.
ok, prova.
È sto roba che si ripete, ciclica.
Questo
Miau miau.
scusa, possiamo
Non sappiamo da sì, ma non so se i volumi sono a posto.
Dopo li sistemiamo. Enrico, intanto mi puoi seguire giù i prof che vogliono essere microfonati con questo. Cazzo di problema. Allora,
Salve, il primo è il... Poi ci sarò io, ok, con l'arancio, è quello che sono nelle lauree, l'info è già acceso, non va spento è acceso, mentre posso dare una mano se serve a lui. Il primo relatore che è fuori di selettore sta facendo la telefonata. Cosa vuole provarlo?
Check, check.
Sì, sì.
Questo nel caso me l'hanno appena data adesso la
Sì.
segreteria, ecco qui Martina, quello avuto che la conosci.
Oh, buongiorno, buongiorno, ma certamente Martina. Sì, guarda, ce l'ho qui in realtà, quindi magari finirò dicendo anche sì, sì.
Sorry for interrupting. Welcome, welcome everybody. Non si
Iniziamo
sente
con
però,
il video
con
di
questi
Foscari.
microfoni non si sente.
Sì, adesso se loro stanno zitti, sì.
Ok.
Oh, how do we do this? I guess we have to go to the, move the slides.
Okay, so after this vibrant introduction of Foscari, I would like, first of all, good morning everybody, and a special welcome to the 34th World Congress organized by the International Society of Bayesian Analysis. Welcome also to Venice, to the Veneto region, and to Italy. And this welcome comes first from the Rector, Lippiello, as well as me, as well as all Foscari and its foundation staff. We are especially grateful to the ISBA and the colleagues in Foscari, first Roberto, Casarin, for having decided to come to Venice to take Venice and Foscari as a conference venue, and for the excellent preparatory work. Yeah, okay, and for the excellent preparatory work. I have been quite impressed by the numbers concerning the attendance to this conference. Well over 800 participants, with a majority of young researchers and practitioners. This is a quite remarkable result. So again, thank you very much to the ISBA, Scientific Society, as well as to Foscari colleagues in charge of the organization of this conference. Sorry. Then,
can you use this microphone, please?
Okay. Then, needless to say that Bayesian analysis, Bayesian approaches, Bayesian tools nowadays are of utmost importance in many sciences, in many fields of science, and Foscari is a good example of this diversity of expertise, of applications of these approaches. It's quite impressive, by the way, to see that almost for more than 2 centuries, the Bayesian analysis was quite silent, neglected by most sciences, but then over the last 50 years, it grew a lot, a sort of explosion, and then the Bayesian analysis and its tools are nowadays used by almost all scientific fields. By the way, I'm also using Bayesian analysis. I'm an environmental scientist, and the applications of Bayesian approaches in the field of environment is increasing quite remarkably year by year. But today, in this short introduction, I would like once again to outline the need to use this conference in a way to strengthen, first of all, individual relationship after the COVID period, then to develop furtherly scientific collaboration and cooperation, and to motivate especially the young researchers and practitioners. So it's very, very important to use this conference also for intergenerational dialogue. That is very, very important because the background of youngest researchers are nowadays quite different compared to the background of senior researchers. So the dialogue is quite fruitful, and this conference may help a lot to strengthen this dialogue and to transfer the experience to the youngest researchers. Then I would like also to report to you the letter, a welcome letter from the president of the Veneto region, Luca Zaia, who addressed to the Rector Tiziana Lippiello the following message. Unfortunately, I will not be able to attend the opening ceremony of the ISBA World Congress due to concurrent institutional commitments. And hereby I wish to extend a warm welcome to all of the distinguished speakers in the Veneto region and in Venice. This meeting represents an important opportunity for discussion and learning the implications of Bayes' theorem as on decisions involving prior information, that is knowledge or assumptions held before observing data. I therefore wish good work to the participants who will have the opportunity to share their knowledge on a branch of statistics whose applications may be extended to different fields from medicine to artificial intelligence, giving the tools for managing uncertainty and risk assessment. Bayesian statistics represents a tool for making informed decisions, accurate predictions, and in the current society that is constantly evolving in every aspect, this methodological approach can undoubtedly be useful. Is concluding by extending the warmest regards to all of you. And then what I can add is, shall this conference unforgettable for each of you, and in addition, have please also some good time in Venice. So thank you again, all of you, for the participations, and have a quite fruitful conference.
So, thank you, Antonio, for the nice welcoming, and welcome to everybody. Welcome to Venice. A lot of friends in the audience. So I will be hopefully very quick in presenting and thanking many institutions, many collaborators, many colleagues and friends helping for the organization of this meeting. A little bit of historical background. We submitted in September 2018 the applications for the proposal for ISBA. ISBA 2022 is not a mistake. This one is ISBA 2022. Then we got selected in November 2018. Then 2020, we received a request for postponing by 2 years again the conference. So we say accept this request, and that's why we have ISBA 2024 in Venice 2 years later. And that would have been impossible without the contributions of many parts. So I would like to thank the head of the department, actually the former and the current actual head of the department, current head of the Department of Economics at Foscari University, then the Venice Center for Economics and Risk Analytics, and also the conference secretariat, Fondazione or Foscari Foundation, which provided the organizational, terrific organizational support for this complex conference. I will explain why it's complex. So we got the endorsement by many institutions. So let me mention a couple of them. The municipality of Venice and the region, Veneto region, you will see we provide support for the childcare service. And then other scientific societies. That's the composition of the organizing committee. Is a very local committee, and we have also an extended committee, which include someone I can see in the audience, Guido Consonni, and Brunero Liseo, Stefano Favaro, Sonia Petrone, Laura Ventura. They provide suggestions and support during these years. And then in the very local, I would like to thank my colleagues, Monica Biglia and Stefano Tonellato, who unfortunately is not here today, and then Christian Robert as well for the supervision. And a special thanks to Isadora for coordinating with the satellite event ISBA Fusion Society, and Emanuele Diverti for the coordination with BASEM, again in Venice. And that's the list of satellite events of ISBA 2024. So special thanks also to Antonietta Mira, who is in the audience. She organized this satellite event in Lugano for attracting people and colleagues from outside Europe. Okay, so that's the idea we got many years ago, to have many satellite events to attract people and then to allow them to participate to ISBA. And then BASEM meeting, we got a couple of days ago, BASEM in Venice. ISBA Cini Foundation is a satellite event we will be discussing about privacy protection. Is a cross-field kind of event. We will have a scholar in law, then we'll have computer scientists, data scientists, mathematicians exchanging ideas about the future of data market, possible data market, European one, for example. That event is supported by Cini Foundation, who provide the site, Ocean ERC project, and Planet for Health project. That's another European project we have in Venice. ISBA Fusion is a sort of a joint event. So next week on campus we will have the Information Fusion Society meeting. That's another international meeting. For organizational issues that I have to admit, that's the reason why we got the satellite. It made sense to have this joint event on Sunday morning. So we'll have some keynote, important keynote and contributors to this joint event with the Fusion Society.
And finally, we had the satellite event organized by University Cattolica of Milan in honor of Guido Consonni. Then childcare and family friendly, that are two aspects we have been working on in this past month, almost a year. I have to thank University of Michigan, ISBA, for supporting the childcare, the municipality of Venice for providing the kindergarten for free. Then we have also this event for dissemination of mathematics, probability, and statistics. So we got this on yesterday evening. Sorry for the weather. We have no power about weather, but I guess many of you managed and to get to the event. Again, we got also a sort of official recognition for official stamp of family friendly. And then let me thanks again Foscari Foundation for the terrific work done in terms of organizations. And about organization, let me remember that your fees include lunches. Someone wrote to ask. So your fee includes lunches, and there are many lunch points. So in terms of organization, you have at least 4 or 5 lunch points. The most far lunch point is this one, the garden. Just take a few steps out of the campus. It will be close, really close to the registration desk. The other lunch points are on the main, street road on campus. Okay, so I'm concluding, and I leave the floor to the ISBA president. Thank you.
Thank you very much. Dear friends, it's my great pleasure and honor to welcome you on behalf of ISBA in this wonderful setting for what I think, if you count from the beginning of ISBA, our 17th meeting. The tradition of ISBA World Meetings was started in 1993, and since 2000 follows a regular 2-year schedule, which was broken only once for the COVID year. By now, we have had meetings in all continents of the world, from Hamilton Island to Kyoto to Cape Town to Viña del Mar and so on. It's a special privilege that we've been invited together in this wonderful place, Venice. On behalf of ISBA, I would like to speak many words of thanks to Foscari University for hosting us on their campus, providing all kinds of support, including financial. I would also speak many words of thanks to the local organizing team, chaired by Roberto Casarin and seconded by Martina Colauto and her team from Foscari, without whose intensive work in the past 2 years, this conference, or maybe even the past 4 years, this conference would never have materialized. Further, I would like to speak many words of thanks to our sponsors and also to our sponsor committee, headed by Antonio Canale, which is not a permanent ISBA committee yet, but has been so successful that we are considering making it permanent. Sponsorship money has been particularly valuable for subsidizing young participants and making childcare possible. My final words of thanks I would like to speak to the Program Council, the Scientific Committee, the Committee on Named Lectures, who worked tirelessly to put together a wonderful program. Special thanks go to the Program Council, Matthias Katzfuss, Sergios Agapiou, Samir Despande, and Sinead Williamson. Sinead had more important events in her life than our conference, but still delivered a mighty job. Before turning the floor over to Sinead, I would like to recall a little history. Here are some people to thank. As I mentioned, the first World Meeting took place in 1993, but also before 1993 there were of course many Bayesian activities, and it depends on how you count whether you can get to 34th meeting, but properly as an ISBA meeting it started in 1993. ISBA was founded in 1992, and The first meeting in San Francisco had nearly 200 participants, 8 invited paper sessions, a cocktail party on Friday, and a dinner on Saturday. And I'm quoting here from a report. I wasn't there. It was considered a great success. Subsequent meetings in the first decade roughly maintained those numbers. And looking back at these meetings around 2000, Arnold Zellner, one of our founders, wrote, and I quote again, "With all this past and current activity, we conclude that the Bayesian era has arrived." Today, about 20 years later, we can conclude he was right, although he may not have foreseen how much ISBA would develop. Our meeting today has 831 participants, 52 invited sessions, 21 contributed sessions, 1 sponsored session, almost 300 posters, and 5 short courses. These numbers almost suggest that the main similarity with the founding 1993 meeting is that a cocktail party and a dinner on Saturday have been retained. We, Bayesian statisticians, ISBA, can be quite happy about how things have developed. Back in the early 90s, the initial acting board of ISBA consisted of many distinguished statisticians, but with Gordon Kaufman, Tom Lennart, and Arnold Zellner, the 3 persons who were become the true founders of ISBA. Last year, the sad news of Tom Lennart's passing arrived. You can read an obituary about Tom by Diego Perez-Ruiz in the first ISBA bulletin of this year, and an interview of Diego and Tom in the bulletin of 2016. It's interesting reading, also if you're young, looking back at an even further past of Bayesianism. In the past half year, we have also lost 2 other prominent statisticians, R.V. Ramamurthy and David Draper. At this World meeting, there are commemorative sessions on Wednesday at lunch and on Friday morning. Consider attending. Finally, I would like to draw your attention to the general meeting to be held on Saturday afternoon. It's a meeting for all members of ISBA to discuss reports on the past and plans for the future. Please attend if possible. Thank you.
So we have a fantastic scientific program for you this week. I'm going to pile thanks upon thanks. There's many people to thank without which this would not be possible. In particular, the scientific committee who worked tirelessly to put together the scientific program, the committee on named lectures, the Savage Award committee, and our prize committees. So the Savage Award and the prizes will be announced at the banquet on Saturday, which is almost full. There are, I believe, a handful more tickets that if you do not have a ticket, I would suggest getting one today. As Ard mentioned, our sponsorship committee have worked tirelessly. Thanks to their efforts, we've been able to support not just childcare, but also the travel of around 150 junior researchers. And I'd like to call out some of our sponsors, our platinum level sponsors. And I'd like to highlight Horizon and Generali have a sponsored session on Friday that I encourage you to attend. Our gold level sponsors, our silver level sponsors, and our bronze level sponsors. So thank you to them all. I'd just like to call out some highlights of the program. So we have the Bruno De Finetti lecture given by Mike Jordan on Thursday. The Susie Barriari lecture is going to take place at the next World meeting due to personal reasons, so apologies, that is not part of the program this year. And we have some excellent foundation lectures starting today with Marina Vannucci, Danny Gamerman on Tuesday, later today, it is Tuesday. Carrie Mengerson, also later today, and Andrew Gelman tomorrow morning. And for keynote lectures, Alexandra Schmidt, Antonetta Mira, Miros Papaspiopoulos, and Johannes Schmidt-Heber. We also have 2 sessions devoted to our Savage Awards on Friday morning, as I said, with the award winners announced at the banquet on Saturday. I will end here because we are already running late, which hopefully will not be a trend for the rest of the conference. Thank you for attending and enjoy the rest of the conference.
So we start in a couple of minutes the keynote session. Marina Vannucci is in the audience. Yep.
Good morning.
Sorry, this one? Yep. Yep. So we start now the foundation lecture. Marina Vannucci. Peter Müller will be chairing.
Peter is chairing.
And the session will be streamed by Zoom in other rooms on campus. So 4A, 5A, 9A, 10A, ground floor rooms. So there will be interacting streaming, so you can receive, Peter, questions from other rooms in Zoom. Okay. Yeah. Thank you.
Bravo! Is this better? Sorry, good morning, now I woke you up, yeah? So it's a real pleasure to introduce our opening talk with the keynote lecture by Marina Vannucci, my fellow Texan, for whom this is also a homecoming back in Italy, although she has been with us in Texas now for so many years. Now as the Noah Harding Professor of Statistics at Rice University. Marina is really, like if you want to identify anyone as a leader in our field, it's Marina. She served as president of ISBA, as chair of the ESA SPSS statistics section, Bayesian statistics section. She served as editor of Bayesian analysis, which is a monster job, and we really appreciate good people doing that. And that was not enough. Right after that, she served as chair of, as editor of CHASA. She served as associate editor for I don't know how many journals. It's just amazing. She has really made she has made massive impact in our field by working on like a great balance of theory and applications, and I think that's the theme of this opening talk. She has contributed a lot in Bayesian bioinformatics, of lately also in neuroimaging, and I think we'll hear some of an application with microbiome data. So I'm looking forward to a wonderful talk. Marina, the floor is all yours.
All right, thank you. So thank you. Sorry, I was told to be seated because of the streaming. So I'll try to lecture from a seated position, although it's a little bit awkward. And so thank you. I would like to thank the scientific and organizing committee for selecting me for this foundation lecture. And it's really an honor to give the opening lecture of this very important conference in such a beautiful place, which is also my own country where I was born. So for today, I've prepared this talk on statistical models for complex problems with applications to science. And as Peter mentioned, the talk is about Bayesian methodologies that I have developed together with many other collaborators and students for specific applications. And I will be focusing mainly on applications in neuroscience, assessing seizure risk based on seizure count data, and estimating brain connectivity networks based on fMRI data. But the talk is focused on the methodologies, and I will use the methodologies to touch upon foundational topics like variable selection and graphical modeling estimation. And then towards the end, if I have a few minutes, I'll also show you an application to genomics, in particular microbiome data, to sort of give you, an idea of the breadth of those methodologies in terms of applications. So let's start from the motivating neuroscience applications. The first one is assessing seizure risk in patients with epilepsy. As you know, epilepsy is it's a very serious disease. It affects 1% of the population. It greatly, severely affects the quality of life of patients because of the unpredictability of seizures. Here we're going to have available data from an electronic diary. So the data are going to be daily seizure counts on a large number of patients. And we're also going to have available a large number of covariates, which we can again extract from those electronic diaries. The goals are going to be trying to estimate what I will define to be an underlying seizure risk at subject level, as well as identify the risk factors that can contribute to seizure risk. We started looking at the data and working with clinicians back in about 2017 or so. And at that time, and even today, I have to say, the clinical decision making was heavily based on just an inspection of the raw seizure counts. But talking with the clinicians, they had this idea that, that seizure counts are really a surrogate measure of what they would call an underlying true seizure risk for every patient. And so there was this idea, this notion that seizures are kind of a stochastic realization of periods of heightened seizure risk. And so we took that at heart, and as as statisticians, we started thinking, okay, it's an underlying process, so maybe we could use HMM, hidden Markov models, to estimate this underlying process. And we tried in 2018 a very simple HMM. We aggregated the data daily to essentially get rid of zeros. We used Poisson distributions. We didn't use any of the patient-level covariates available, just a simple estimation of the raw counts. But already with that very simple model, we obtained very encouraging results, and actually we were able to validate the results against predictions from epilepsy clinicians, so it was quite encouraging. So the model that I'm going to show you today is kind of the full-blown development of that very simple idea. We now look at multiple subjects, and we incorporate covariates, and there is an element of variable selection for the identification of the covariates that are important in estimating or predicting seizure risk. The second application, apparently quite different from the first one, is about brain connectivity estimation based on fMRI. In neuroimaging, we use fMRI data to estimate two types of connectivity, functional and effective. So connectivity refers to the way that different brain regions interact with each other. And so we think about functional connectivity when this interaction is simply a correlation or is an undirected type of interaction. We think about effective connectivity when there is a directionality to that interaction. Today I will be focusing mainly on functional connectivity, so undirected connectivity. I think I have one slide on effective connectivity at some point. So here the idea is that you have the subject in the scanner and you measure data for like 30 minutes or so. The subject in the scanner might be alternating like periods of rest to periods where he or she is instructed to respond to a stimulus. And so the data look like time series data, right? On a single subject, you would have a number of brain regions, say 100 at most, and you measure time series, a multivariate time series on an individual subject. The idea, you want to estimate a graph, right, in statistical terms, so you want to understand how these brain regions interact with each other. There is this fundamental conviction that connectivity is dynamic, so that the graph that describes the interactions between the brain regions is not static. And I mean, it makes a lot of sense because you think about your subjects alternating periods of rest with periods where he or she is engaged in a task. And so naturally you are thinking about connectivities in your brain that change, right, with the state of the experiment. So here, again, the idea is to estimate a graph, dynamically that changes along the time, and then that changes a sort of discrete time points. So again, you, as a statistician, you start thinking about HMM as a way of describing this underlying process. And this is what, again, we tried with working with Michele, Guindani, and others back in 2018. Again, we tried a very simple model at first, like an HMM on a single subject, not using any of the covariates. We have covariates available here on the subjects as well, and we got quite encouraging results. So with Michele, we have pushed forward this line of research, and the model that I'm presenting today is, again, the full-blown model that now looks at multiple subjects, incorporates covariates, and has aspects of dynamic and variable selection. Okay, so as I said, I'm going to use these applications and motivations for the methodologies. As you can see, although they're very different applications, they have some common goals, right? Clearly, there is this idea of like an underlying processes that we want to estimate in both applications. And so I will be using HMM. One can also think about state space models, but today I will stick with HMMs. There is this idea of measuring covariates, external information, on the patients, and this idea that covariates are important, and it's important to identify the covariates that relate to the underlying process. So there is an aspect of variable selection, and at least in the second project there is also an aspect of graphical model. So we'll be going through the methodology, and as I said at the beginning, I will sort of highlight foundational aspects of these topics, particular variable selection and graphical models. So let's consider the first application. This is a visualization of the model that we have developed. So we have at the level of the data, we have the seizure counts, the daily seizure counts. There is overdispersion in the data, and actually the data include also a lot of zeros. So we'll be using negative binomial and actually zero inflated negative binomial for the emissions of my HMM. And then we have the sort of a hidden layer where we are envisioning risk state, right? So the subject might move from a low risk state to a medium risk state and then transition back to the low risk state and so on and so forth. And then we have available very many covariates. We have sort of standard characteristics on the subjects like age, sex, and other demographics. And then we have information on things like medications, as well as many seizure triggers. They are considered to be triggers. And then information on the type of seizures, the time, the duration of the seizure, the etiology, and so on and so forth. And so we want to incorporate these covariates into the model in order to identify what could be the risk factor that contribute to the underlying seizure risk of the patients. We want to incorporate the covariance in two different portions of the model, in both what I call the emissions and the transitions of the HMM, because we want to be able to understand if a given medication contributes to the transitioning of the subject from a low risk to a medium risk state, for example. And then given that the subject is on say, the medium risk, we want to understand how the covariates affect the daily number of seizures of that patient. Of course, we want to allow covariates in either or both the emissions or transitions. So it's truly a variable selection problem because you want the model to discover that information. Okay, so this is practically the model. So now I'm just going to attach a couple of formulas to this plot. So given the data y, I, t, number of seizures for patient I at time t, we introduce the xi-it, the latent risk state of patient I at time t, and then we model at the level of the transitions, we model the transitions of the HMM by a multinomial logic link that incorporates the covariates here there. So in this way, we introduce a set of parameters, those beta k prime k, that determine whether covariates are associated with worsening or improvement of seizure risk. So we transition, right, from a state from a given state to another state with respect to transitioning from that state to a baseline state that we will have to fix in the application. As Bayesians, we know that having a multinomial logic link nowadays is particularly nice when it comes to implement MCMC because we can use polygamma data augmentation. Then we're going to also, at the emission part of the model, we're going to consider a zero-inflated negative binomial distribution, as I already said. So that's the formula here. So it's a mixture of a spike at zero and a negative binomial. In order to incorporate the covariates in this emission, we're going to reparameterize the distribution in terms of dispersion of a dispersion parameter and a subject and state dependent success probability. And then we're going to let that probability depend on the covariates. Again, the same set of covariates. With a multinomial logic link, we introduce a second set of parameters, rho k, which are state-dependent regression coefficient. And we can easily move back and forth between the two parameterizations, so essentially have the mean as a function of the covariates. So this new set of parameters now determine whether a covariate is associated with increase or decrease in seizure frequency, given that a patient is in a given risk state. Okay, so now this is the model, and the next step is to do variable selection. So we have two sets of parameters, the betas and the rho k's, and we want to do variable selection. Bayesians can do variable selection in a number of different ways. In my career, I've sort of stuck with this class of priors, spike and slab priors. So I'm going to use this part of the talk to say something about this kind of as a foundational part of my talk, to say something about spike and slab priors. I guess we're all familiar with these priors, but anyway, they were proposed in the sort of standard linear regression settings. And the idea is to introduce a latent indicator, gamma j, my notation, that index whether a variable is important or not. And then there are two formulations of this prior in the literature. One is the discrete spike and slab, or we call it nowadays discrete spike and slab. The other one is the continuous spike and slab. With the discrete spike and slab, we use the indicator to impose a mixture prior on the regression coefficient beta that is a mixture of a spike at zero, so a Dirac at zero, and a slab distribution, which is typically a Gaussian distribution. In the continuous version of the prior, the prior distribution is a mixture of two normals, where the first normal is tight around zero, and the other is the slab, which has a larger variability. And then typically we have a prior on the indicator of the variables, which in the simplest form can be as simple as independent Bernoullis. I'm going to say a few words about these priors, but before I do that, I want to point at a book which I have edited with Mahalet Tadesse back in 2021. It's a handbook of Bayesian variable selection, and it reviews lots of different priors and methods for variable selection. The first maybe 5-6 chapters are devoted to spike and slab, continuous and discrete spike and slab. I will say something about this, the content of these chapters in the next couple of slides. But there is much more in the book. We touch upon continuous shrinkage priors as well as extensions to various modeling like causal inference, state-space models, and there are also chapters on graphical edge selection and graphical models, which is another topic that I will review later on in the talk. And the chapters are contributed by experts in the field. So as I said, the first 4 or 5 chapters of the book cover spike and slabs, both discrete and continuous. So I'm just going to say a few words about these priors. In the typical regression setting, we sort of were used to marginalize out the regression coefficients and just work at the MCMC level, just work with the selection indicator, the gamma J. This is particularly appealing when we can do that because we can use very simple stochastic search algorithms to search the posterior space of all possible models. Later on, we have sort of tried to move away from simple regression and simple conjugate settings. And I think at that point, at least in my vision, there has been a little bit of misconception in the literature because I often see that nowadays people seem to think that in order to use the discrete spike and slab, which is the one with the Dirac delta at 0, in order to use it for settings where you cannot marginalize the regression coefficients out, you need to use a reversible jump. This was true at the time, in the early 90s, when we came up with this prior construction. But there's been some developments in the literature later on, particularly Gottardo and Raftery in 2008 with a paper in Journal of Computational Graphical Statistics. They were able to formulate the reversible jump as a mixture of singular distributions. They were not thinking specifically of spike and slab, but the spike and slab is a special case of what they did. And so if you use their idea and their algorithm, when you cannot marginalize the regression coefficients out, what you have to do is simply to sample the coefficients and the indicator jointly. And of course, you can write the joint distribution as a product of a marginal and a conditional if you can, and do the two sampling like that. But essentially, you don't need reversible jump, and it's just a standard Metropolis or standard Gibbs according to what you have available. So that is the trick that I've been using a lot in the models and that I'm using in the models that I'm showing you today. It allows you to handle non-conjugate and non-Gaussian settings quite easily. The book also covers theoretical aspects of spike and slab. Initially, there was a lot of development on continuous spike and slab because you work with the two normals, so I guess some of the theoretical development may be easier or at least more established in that framework. And then there's been a kind of breakthrough work in 2015 by Castillo and others, where they essentially were able to also come up with theoretical results for the discrete spike and slab. So now we also have theoretical framework for the discrete spike and slab. Both priors are very useful in applications. With respect to shrinkage priors, I often get this question. So with respect to continuous shrinkage prior, like lasso prior or horseshoe priors, the spike and slab has the ability of with the introduction of that indicator, that binary indicator, you have the ability of calculating a posteriori what you call marginal PPIs, the marginal posterior probability of inclusion. Right? So you have that probability, and it's a meaningful probability, and that you can threshold to do your final selection. Unlike continuous shrinkage priors, where you have the posterior distribution of your parameters, so you are thresholding that posterior distribution. In my view, it's a more difficult thing to do. These spike and slab priors are also quite scalable. Of course, shrinkage priors are more scalable because you don't have the indicator. So having the indicator has pros and cons. And the cons is certainly in the computation because it's more difficult to handle the space of all possible models. But there are methods that have been proposed to try to scale up those priors, both in terms of EM and variational base. There's quite a bit of work with variational base with spike and slab, including discrete spike and slab. I hope someone will talk about it at this conference. In my applications today, I'm going to use the discrete spike and slab. It's somehow the prior that I've always used in my work. The continuous spike and slab has the two variance parameters. They need to be tuned in applications, and there is always a little bit of sensitivity on difficulty on how to do that, and therefore I personally prefer the discrete spike and slab. Okay, so back to my model. So the parameters on which I want to put spike and slab priors are these two sets of coefficients, the regression coefficients in the transitions and the coefficients in the emissions. And so we're going to put discrete spike and slab on both of them with simple Bernoulli priors on the indicators. And then for MCMC, I'm not going to spend much time here. I've essentially already told you we are using this joint update of the parameters with the indicators, and we are incorporating the polygamma data augmentation in that update, and then the rest is kind of straightforward, knowing the literature on HMMs. I will show you directly results on the applications. If I don't get to see at the end, I want to say that every paper that I'm citing during the talk has extensive simulation studies with extensive comparisons with competing methods, both frequentist and Bayesians. But today in the talk, I'm only focusing on the applications. So as I said, we have data available from an electronic diary. It's called Seizure Tracker. Is I believe, the largest electronic diary that we have in the US. Epilepsy is a very heterogeneous disease, so it doesn't make sense to just analyze everything that you find in the diary, but it makes sense more to look at specific type of epilepsy. So today I'm going to show you results on 133 patients with Dravet syndrome, which is a very aggressive type of epilepsy. And we have data that span from 2007 to 2020, so quite a bit of data. We were able to extract 37 covariates that include 23 classes of medications, 10 seizure triggers, and 4 patient characteristics. If I get questions about prior specification, I can answer those at the end. We are not going to try to learn in an intelligent way on the number of states of the HMM. We are simply going to learn that based on DIC, so in a very simple way. As Bayesians, we know that you can do much more and perhaps think about a prior on K. Here for the application, DIC gave K equal 3, which was very nice for our collaborators because they can think about a low risk state, a medium risk state, and a high risk state. So to them, that's just great. The output of the model, I'm just going to give you a couple of snapshots of the output. So it includes plots of this type, which are that show the estimated sequence of a risk state for a particular subject. So you see here this subject transitioning from the low to the medium, back to the low, and then the medium, and eventually to the high risk state. And then you see the continuous line is the estimated number of seizures for this particular subject, and the dots are the data. The plot below is the one that we had obtained back in 2018, where we're not using the covariates, so you can see the fit is quite better here. And then together with this plot, we have the output from the variable selection, and so we can produce marginal posterior probabilities of inclusion for the covariates that are important for the transitions, as well as covariates that are important for the emissions. So given for the that affects the expected number of seizures given that the patient is in a given state. And for the clinicians, we can produce tables, so together with the selection, we can also produce tables with the estimates of the corresponding coefficients so that you can actually assess, right, the actual effect of the covariate. Is it a good covariate or a not good covariate? And so we give tables of this type. And again, I'm not going to spend time on the actual, clinical relevance of the work, but the idea of this model is not so much to learn something about epilepsy, but to give to the clinicians a tool that can be useful for them in helping, improving the quality of life of their patients. Because a clinician can sit down with a patient and look at the estimate of the sequence, hidden sequence states, and look at the effects, decrease or increase of the different seizure triggers, medications, and so on that he's taking, and kind of adjust the diagnosis of the therapy for the patient. The actual statistical model is published in the Annals of Applied Statistics, but we have pushed this technology quite a bit together with our collaborators, and we have a few clinical publications as well. So that's all I want to say about this application, also because I don't want to use too much time. So I'll move to the next one, which I've already introduced, which is dynamic brain connectivity. So here, the application seems quite different, right? So we have data now on an individual subject, which have data that are multivariate time series, fMRI responses measured on a number of different regions, and we want to understand how these regions interact with each other via the estimation of a graph, and we are thinking that this graph is not static. It's a dynamic graph that evolves throughout the experiment. We also have covariates on the subjects that we want to incorporate. So if we think about the framework that I just used, what changes is, first of all, the emission distribution, right? Now we have continuous data, multivariate time series, so the emission will become a multivariate Gaussian distribution. But then we can think about trying to incorporate covariates in the same way as we have done in the previous model. Today I will just incorporate covariates in the transitions, and it will be just one covariate in the application. But coming from the previous model, from a methodological point of view, I guess you can see how these models can be pushed forward. The idea, the HMM here works particularly nicely because it allows us to estimate a graph that can repeat over non-contiguous time points. So you can indeed model this idea of a subject that is at rest, and then does a task, and then moves back to rest, right? So you have this graph that can potentially repeat themselves over non-contiguous time points. So the HMM is really nice here. The sort of the new aspect with respect to the previous application is the graph, right? So now I'm going to insert another sort of foundational part of the topic of the talk by reviewing a little bit Bayesian estimation methods for graphical models. With graphical models, so we have a set of nodes, and those can be linked by edges, and we say that there is no edge between two nodes if we're thinking about the variables being independent given all the others. And already, if you look at the graph, you look at the edge, and you see absence and presence of an edge, so you start thinking about, okay, I can use an indicator here, right? A binary indicator with absence and presence of an edge. And so now if I find the parameter, right, I can start thinking about spike and slab priors, okay? So let's see if we find that parameter. We're going to be working with Gaussian graphical models because the data are continuous, multivariate. And the Gaussian framework is particularly nice because in the multivariate normal distribution, there is a very nice correspondence between what we call the precision matrix, which is the inverse of the variance and covariance matrix, and an underlying graph, in that a zero element in the precision matrix corresponds to an absence of an edge. Okay? So now I have my parameter, right? I have the indicator of presence and absence of edge, and I have my parameter, which is quite a complex parameter because it's a precision matrix, or it has restrictions like have been positive definite. So in the in the literature, in the Bayesian literature, indeed, so there are a number of different priors that we can use. They're sort of like, go in parallel with the sort of spike and slab priors and the literature in variable selection. So that's very nice. And going back to the book, the handbook does review that sort of parallel in the literature. And so there are priors that indeed mimic what we could call the discrete spike and slab, and those are the G. Wishart priors that enforce exact zeros in the matrix. And those are, though, very nice, but computationally quite challenging to use, because having those zeros makes computing prior and posterior very hard, because we cannot calculate we don't have the normalizing constants available. So these priors are nice, but in my experience, they don't scale very much. I've used them for small graphs, like 10, 12 nodes. I also want to say, though, that I've seen a recent paper in the literature by Maria De Iorio and others, where they have improved on the sampling algorithm for the G priors, and they seem to be able to scale these priors quite a bit. So I'm going to look at those at their work more closely. Then there is something that could be the equivalent of a continuous spike and slab that we've seen before for graphical models, which was proposed by Hao Wang in 2015. And so here the idea is to have exactly continuous spike and slab, so a mixture of two Gaussian distribution on the off-diagonal elements of the precision matrix. So we are not enforcing zeros, but we gain in computational efficiency of this prior. This prior can scale up to hundreds of a few, well, let me say less, about 100 nodes. And there are also nice results available in the literature on consistency results for this prior. There is also a class of shrinkage priors. There is a graphical lasso and also a graphical horseshoe prior, which is the one that I'm going to use today for the application in neuroimaging, although I'm fond of spike and slab, but I'm going to use the graphical horseshoe prior, which actually I've found to work very, very well. So this is graphical horseshoe prior proposed by Lee and others. It is nice because of the flexibility of the parameterization. There is a global shrinkage parameter as well as local shrinkage parameters that allow to shrink the individual of diagonal entry towards zero. So I think that makes the prior work very nicely. And there are also available block Gibbs sampling algorithms that we can use. Okay, so having reviewed this, I'm going to move back to my model. So again, here the data, YIT are vectors of fMRI bold responses at R regions of interest for an individual subject. And the likelihood is a multinomial on an individual subject is a multivariate Gaussian distribution. And we're going to have graphical horseshoe prior on the precision matrix. And then underlining, there is the HMM, and we're going to impose, on the transition probabilities, we're going to impose this multinomial logit link where we incorporate the covariates. Again, in the application, I will be using only one covariate, but here you have the expansion with multiple covariates. You could think about spike and slab priors on those coefficients, rho S, to select the covariates. But again, I'm not going to do it today, but it's a possible future application of our methodology. Okay, I'm going to skip. The parameterization is slightly different here, but I don't think I'll have the time to go through things. And one thing which is peculiar about this model is the way that we've made it multi-subject. So we essentially have allowed a sort of an ANOVA type construction on the parameters of the transition probability. So they're assumed, they're like random effects, they're assumed to be Gaussian and centered in population level parameters. So we can fit the model to multiple subjects at once and have both subject and population or group level parameters. Okay? Being that the likelihood that a single subject is already multivariate Gaussian, this is kind of a cheap way to make the model multi-subject. And then MCMC, again, polyagamma data augmentation and sort of like straightforward algorithmic methods for HMMs and for the graphical horseshoe prior. I'll skip this and I'll show you the application. Okay, so the task is quite complicated. So we have fMRI data on a hand grip task on multiple subjects. And together with the fMRI data, we also record the pupil dilation. And the task is an attention focus. And so we know that, that we dilate or shrink the eyes, right, when we focus on something. So this is quite a meaningful covariate that is measured throughout the experiment. We are going to be looking at 31 ROIs, selected out of a total of maybe about 100 ROIs, regions of interest, if I did not say that. And the selection of the 31 is done based on selecting those regions of the brain which we know are implicated in attention and focus, which is the task here. Among these 31 ROI, there are 2 of them which are of particular interest to our collaborators because they have been implicated in neurodegenerative disorders like Alzheimer and Parkinson. We have 27 subjects that perform a hand grip task. And the task is as follows. The subject is in the scanner and somehow they are able to reach to a squeezing ball which is placed by their side. And then they are at rest, and then at some point they are instructed to grab the ball and bring the ball to their chest. And there are 2 different conditions. In condition 1, which is called sham, that's all they do. They just bring the ball to the chest. And then in the second condition, which is the active session, the active condition, they're also instructed to squeeze the ball. Okay, so that's this. The task, as I said, the dilation, pupil dilation data is collected at the same time, and I'll skip prior specification. I'll show you again just a couple of snapshots on the results. So the model will produce connectivity graphs, okay, so estimated connectivity graphs at different states. Again, we use DIC. I think we fit the model for different values of K, and it turned out that K was the optimal because for more than 3 states, they collapsed down to 3, if I remember correctly, okay. And so 3 turned out to be the optimal number of states. So the model will estimate 3 connectivity states, state 1, 2, and 3. If we look, for example, at the connectivities in state 1, we can see a lot of those connectivities that we would expect in a subject doing a kind of a focus attention task. Okay? And in fact, if we now pair this plot with the inference on the estimated state transitions for the 37 subjects that we have, we can see that, because we know how the experiment evolves, here the sequences are aligned such that the first half refers to the sham condition and the second half to the active condition. And so because we know where the task happened, now we can see that state 1, which is the orange state, relates to when the task happened, when the subject is instructed to grab the squeezing ball. Okay? So state 1 is the task, so then going back to the network, so now the network for state 1 is the network that captures the connectivity of the subject when the subject is performing the task. And then there is something very interesting about the other 2 states, which is kind of difficult to see, but I'll just describe it in words. The state 2 and 3, they relate to resting state, but we notice that there seems to be the relative occupancy in state 2 appear to be higher when subjects are in the active state. Okay? So meaning that state 2 seems to be associated to a rest state that subjects seem to migrate to in the active condition, and state 3 in the sham condition. Okay? So again, so now it makes sense to go back to these 2 graphs, the 2 states, and think about, okay, the resting state is the connectivity of a subject that is expecting to be engaged in an active task, versus state 3 being in a sham condition. Okay. So again, just snapshots of what we can do with these models. There is a little bit more in the paper, also about the inference on the actual covariate that we use, but I'll skip everything. And the paper is just appeared in PLOS ONE. For those working on fMRI data, I also want to highlight a parallel in the fMRI literature on models for effective connectivity, which highlighted at the beginning of the talk, right? So this type of connectivity, undirected, is what we call functional connectivity. But clinicians are also interested in effective connectivity, so having arrows to those edges. And so there is a parallel in the statistical / neuroimaging literature. There is a parallel literature on effective directed brain connectivity, which we solve by vector autoregressive models or switching vector autoregressive model to get this idea of the HMM formulation. Okay? And so here you can think about a vector autoregressive model. Oh, okay, great. And now you will be selecting parameters of the vector autoregressive model to estimate your directed connectivities. So you can think about, again, spike and slab priors to do this. Vector autoregressive models are highly parametrized, so computations become a huge problem. So there are variational inference approaches that can be used, but a recent trend in the literature that I've seen is tensor modeling. So there is quite a bit of development in tensor modeling for vector autoregressive models, with contributions by, like a recent contribution by Michele and Sonia Petrone, as well as many others. So I just wanted to highlight that. And now I have, a few minutes, which is just what I need for the last part of the talk, which is on the microbiome application. So I want to show you the sort of, the full breadth of these applications, so this type of model, so that you don't think that they are just confined to these neuroimaging applications. And in doing that, I want to sort of push on one aspect, methodological aspect of the models, which is that the incorporation of the covariates. Right? So covariate-dependent modeling is quite important. Being able to bring covariates into the model, being able to select covariates as, for example, in the first application, to identify risk factors for seizure risk. But in what I was doing, I've always used kind of sort of linear settings, right? But if you think about covariate effects, one may think naturally that the effect might not be linear, and actually that a non-linear effect could be of interest to collaborators even more than a linear effect, right? So this could be where the real interest is in the data. Statisticians use varying effects models as a possibility, okay, to capture non-linear effect. And so I'm going to be using this framework where the idea is that we have an outcome, we have a set of predictors, so X and Y. But so the idea is that the relationship between X and Y could be modulated by other covariates, right? So could be possibly non-linear, modulated by other covariates, which are going to be the Z. And the sort of the linear formulation of the model is the one that you see in blue. I'm going to be trying to show you an application of microbiome data, again, just to show you something different. So here the idea is that the available data are going to be observations on microbiome as abundances of microbes present in our body, which you can collect as simply as with a sample of saliva. There is going to be an interest in understanding how these microbiome features link to each other. So there is an aspect of estimating a graphical network among the predictors, as well as understanding how the microbiomes affect a possibly disease-related outcome, which in my application is going to be BMI, so just a very simple outcome. And then we want to see or understand whether this relationship can be modulated by subject-level covariates. So we are thinking that there is variability in the impact of microbiome features on the outcome across different subjects. So we want to model that variability. I only have one slide on the model. Again, I'm not going to say much about this, but I'm just going to highlight the methodological points, I guess, with respect to the previous models. So the idea here is to factorize the joint distribution of x and y as the product of the conditional times the marginal, and then the conditional of y given x is going to be a very ineffective regression model, and the marginal on x is going to be the Gaussian graphical model, so again, the microbiome data. And then we want to do variable selection on the axis and on the z, so we're going to incorporate spike and slab priors in the two parts of the model. We're going to reparameterize the very ineffective regression coefficient as the product of an indicator and a continuous parameter. Then we're going to have a Markov random field prior on the indicator and a Gaussian distribution on, on the continuous, Gaussian process on the continuous, on the functional regression coefficient. This formulation of the spike and slab is slightly different from the one I used before, and again, for those working in the field, the advantage here is that you can easily marginalize the beta, and this is particularly important with Gaussian processes, okay? So because we are putting a Gaussian process on the functional regression coefficient, this sort of parameterization of the spike and slab allows to integrate the functional coefficient out. So with Gaussian process, this is a big deal in terms of doing MCMC. And then we can always learn on the regression coefficient, the functional regression coefficient via the predicted distribution, so we're not lose much. Okay, and just a snapshot on the result, and then I think I'm done. So this is what we learned by applying the method to Combo. Combo is actually the name of the hotel that I'm staying at in Venice. But it's also, okay, I didn't notice this until now. So the Combo study, so we have available the data from this study, 69 taxa as predictors, 98 subjects, and 3 covariates, and the outcome is the BMI. So we see that we learn, right? So we learn a graph among all the taxa, the microbiomes that has 108 edges. And then through the variable selection priors, we learned that there are 11 taxa, 11 microbiomes, which are selected as having an influence on the BMI. And then we can learn for each one of these selected 11, we can learn whether their relationship is affected by some of the covariates and if it is linear or non-linear. And I'm just focusing, for example, on this one, the plot in the middle. We can see that for that taxa, there is a protective role of this covariate, which is the dietary fiber intake, because the beta is generally negative. And we can also see that the relationship is different by sex, because the 2 lines that you see in the plot is male versus female. So that little plot there is a lot of useful information for our collaborators. And the paper is under revision for biometrics. So I'm basically done. So just a summary conclusions. So neuroscience, neuroimaging, as well as genomics are very important applied area for Bayesian methodologies. And I've shown you methods that have aspects of spike and slab variable selection, as well as estimation of graphical models, HMMs, and many other interesting aspects. Methodologies go beyond the Gaussian world. And a lot can be done from a computational point of view. I didn't spend much time on this. We always try to, optimize the MCMC as much as we can, and then once the MCMC takes more than 12 hours to run, then we resort to a variational inference or an EM or whatever is available. Okay. And I already said about simulations. I'll acknowledge the students involved in this work: Emily Wong, Jaylen Lee, Ryan Warnick, and Jan van Ren. And then for the long list of collaborators, nowadays I'm using this cloud of words where the thickness of the word is proportional to the number of papers that the person has written with me, and I'm looking in particular at Michele Guindani. And then so for this work, so huge acknowledgements to Michele, to Sharon Chang and Christine Peterson, Francesco Stingo, Mahalet Tadesse. And also I want to acknowledge Phil Brown, who is in the audience today, and he was my postdoctoral fellow many years ago. And these are the references. Thank you.
Thank you, Marina. Any reactions, comments, questions? Judith.
Hi, thanks for the talk. I was just out of curiosity, when you use the spike and slab priors in your complex models, how stable is it to the initialization of the algorithms? Do you have to do a lot of tries, or is it easy?
No, it's very easy for the actual spike and slab. But yeah, when you do the stochastic search, you have to initialize. You can initialize from a random set of variables, and that will be your starting model, right? So it's very, very easy to do, and it doesn't depend on. You can do multiple if you have. You can do parallel MCMCs and initialize each one of them from a different model, just to make sure that that is not affecting the final output in terms of initial values. Was your question about sensitivity? No. Sensitivity, I mean, spike and slabs, yes, the sensitivity is to the sparsity that you induce via the prior on the indicator, which I often consider an advantage because, again, it's a way that you can induce sparsity. It's a way that you can say, I expect my final model to be around 10% of the actual number of variables. So I always find that an advantage. But yes, so there is sensitivity to that parameter, the sparsity parameter of, say, the Bernoulli or the Markov random field prior that you put on the indicator.
Wonderful work, Marina. Very nice talk. In most of the applications you presented, and in application across biomedical field at least, data arrived at the desk of a Bayesian statistician after they've already been pre-processed, normalized, scaled. There's a long stream of manipulation before the Bayesian analysis actually begins. And I wonder if you have, and sometimes there are implicit, integration of nuisance parameters that go on in there, or correlations that get lost. Where do you have any words of wisdom about where the data wrangling should end and the Bayesian analysis should start, and what effect that has on the complex modeling that you described?
Yes. No, it's a very good question, and it's a very difficult to answer. It depends, on the seizure risk. We were able to actually get to read the data directly from the electronic diary. So we did all the pre-processing ourselves, and that helped a lot, right? Because together with the student, but also a couple of clinicians, so you could see that we were able to understand what we were doing. With fMRI data, that doesn't happen because collaborators do a whole lot of pre-processing before they give the data to you. So there is, a lot of literature on whether, you should incorporate. At some point, we were incorporating long memory type of noises in this sort of models, and then sort of find a way to processing the data so that noise, which they call the pink noise, is no longer in the data. So I don't have a good answer. I mean, you have to talk to them a lot and just be able to try to understand what they are doing, and sort of, try to incorporate aspects in the model aspects of that pre-processing. But I mean, I don't have any wisdom, any word of wisdom besides talk to them as much as possible.
And maybe ask Giovanni for words of wisdom. So I don't know, how would we get questions from the remote side? Like there are people in another room watching us over video, right? Can they ask questions? Or so if anyone over there wants to ask, we can probably hear you on the loudspeaker. Just trying to encourage folks in the fan room over there, if they want to ask something. There's some public viewing going on the other room. No. Anyone here? Any more questions, comments before we break for coffee? I know we are a few minutes over time, but she started only 10 minutes late.
Thank you for your nice talk. I was wondering, by talking about the data, I was wondering microbiome data, they are also highly zero inflated. and they sometimes are under-dispersed, and of course, obviously, over-dispersed. So in your last project, I was wondering how these things feature of microbiome data you incorporated in your model?
Yeah, that's a very good catch. Yes, so we did not. We transformed the data. We log transform the data to be continuous. So this is often done in the literature, not something that I would agree with, but for that model, that's what we did. And in fact, you see that we have a Gaussian distribution, right, on the axis. So those are log transformed. You can modify this model because nowadays there are also graphical models for count type of data. So yeah, and that could be like, a possible future extension of this model. Try to model the microbiome as counts. Good catch.
And one more last question before coffee.
Nice talk. So my question is, most of your work, I think, for brain connectivity was for functional connectivity. And you mentioned about the prior you use for sensitivity, you use it 20% or something. So is it possible to use a structural connectivity also as a prior for your functional connectivity?
Oh, yes, and actually with Michele, we have done that too in a previous work, yes. So you can have, in the indicator of the spike and slab, instead of a simple Bernoulli, you can use a Markov-Randolph field prior, and you inform that prior with structural connectivity. So you say, a priori, I'm thinking that there is functional connectivity if these two regions are structurally connected. Yeah, that actually, those priors work very well in those applications. Yeah, thank you.
Well, thank you. Then let's thank Marina one more time. Thank you.
Thank you.
And we'll break for coffee and we reconvene at 11 back here for Dani Gammerman's foundation lecture. Thank you, Marina.
Are you able to be
Thanks again for your continuous support. It was very different than how we used to. I know. The last word that it was raining, I don't know if you left earlier.
Yeah.
So the magician, I forgot his name, he stayed and he did more magic.
Oh, that's so nice. No, we were in the back, and so we were kind of at the early part leaving, and they just pushed everybody, like not pushed, but they were like, "Oh, you have to go." I was like, "Oh."
Si vede che chi parla ha una voce fastidiosa.
Non ho capito.
Si vede che chi parla ha una voce fastidiosa.
Perché?
Perché non vuole che sentito parlare.
Very awake at all times. Like more awake after coming to Yeah, she doesn't understand about time zones.
Too high dimension.
Yeah.
Go back outside.
Push this here and turn on the mic.
Also, the microphone is better in this way.
Yeah, it's the sound is this way, otherwise the
The reserved seats are for who?
For my wife? For the boss.
Leave one for my wife.
Yeah, okay. But you
Otherwise, you'll be in trouble.
But I need that you tell me she is my wife. Because I can, okay? And you need
problema è che se qualcuno parla dopo lo sente sale. No, non è in condizione, perché come ti spiegavo ieri, Zoom, l'audio di Zoom segue il video. Se questo PC è aperto che sta proiettando, l'audio è aperto. Dobbiamo essere sicuri che non ci sia nessuno che va fuori di perché se no dovremmo dargli, se è che io non ho un PC da darti. Anzi no, io sono il mio. Apriti il mio. Però allora dobbiamo comunicare a tutti che le domande le facciano in chat, quindi deve esserci. No, basta che facciamo pubblicare, c'è una domanda. Ok? Io autorizzo. Però a quel punto me lo devi dire, io devo switchare sul sito. Ah, ok. Dovreste seguire. A meno che. Allora, è da capire come farlo, perché la domanda o le gestiamo in chat, forse è meglio ancora gestire in chat. Perché comunque se le vogliamo le domande fatte comporta chi è nelle altre sale si alzi, vada al tavolo, perché non ci sono gelati, vada al tavolo e faccia la domanda, forse è più pratica che se ci sono loro domande le fanno a ragazzo che è di sala che lo scrive in chat e tu le vedi live. Dimmi tu se può essere più pratico o Martino. Le facciamo fare in chat e l'operatore le scrive. Quindi sappiamo che dalla sala 10A c'è la